Our next speaker is Luke Achenie. He's a professor in the Chemical Engineering Department at Virginia Tech. He holds a diploma from Massachusetts Institute of Technology from 1981. His research interests, as I was reading, there are many: multi-scale molecular modeling, machine learning, blood-brain barrier modeling, pharmacokinetic modeling, uncertainty analysis, process design, and math programming. So the floor is yours.
Okay. Thank you very much for Achenie and Dr. Shi, who invited me to this conference. So the very first one in Bangladesh, I attended, and there was another one. The second one was in Mexico, I believe, on a very nice beach. It was not there, unfortunately. Okay, but this time I'm able to make it. So I'm going to talk about. Let's try this. Oh. So let me break the ice a little bit and tell you about where my university is. I'm at Virginia Tech. So, let's see. This is the state of Virginia. Okay. And this is Washington, D.C. Most of you know it. We are in Blacksburg, Virginia, very close to the West Virginia boundary here. So we're over here. And from here to Washington, D.C. is about 4 hours drive. I drive that a lot because I have relatives in Washington, D.C. These days I don't do that anymore because my car broke down along the route 81. And so I'm a dedicated train rider right now. I take the Amtrak. So, this group, as I get used to this, okay, good. So, Blacksburg is surrounded by the Blue Ridge Mountains on the Appalachian Tour. It's very, very beautiful out there, especially during the summer. Okay. And then, there's during the fall, you see this kind of view. This is one of my favorite trails. This trail is about 4 miles. And so during COVID, well, I use that as an excuse to walk on that trail, okay, 4 miles. Very good exercise. The other thing also is, this is not me, it's somebody else, but I actually have a picture with me on top there. And one of the reasons I wanted to do that was to cure myself of the fear of heights, all right? So I'm no longer as fearful of heights as I used to. Okay. And so this is our building, the Goodwin Hall, which is we share with mechanical engineering and engineering education, this chemical engineering. And so, okay. So let's look at hydrogen. I'm looking at this picture here. Okay, and there's a Californian dot curve. So during the day, solar energy is abundant. Okay, and so that can be used to convert solar energy in a form that can be stored. Okay. And in the evening, solar is sparse. Okay, so you can see basically this curve is saying exactly that. So one of the forms of storing energy for later use is through hydrogen. Okay, so hydrogen as an energy source, and it needs to be stored for long durations for use in peak demand and seasonal energy balancing. Okay. And how is it produced? It can be generated from electrolysis using excess renewable energy or electricity during peak hours. As fuel, hydrogen can be used in stationary fuel cells for power generation. And metal organic frameworks is an alternative storage medium. It's a relatively new storage medium, very fast growing. Look at carbon dioxide. Now, this picture here gives us the global carbon dioxide amount. This is from 2002 to 2022. So over a period of 20 years, we've gone from 365 to 435. Okay, that's something interesting. So the production of carbon dioxide can be generated from, there's a lot from transportation systems, okay, human activity of course, industrial production system, coal burning power plants, fossil fuel sector, etc. And we know that it's not good for the environment because of greenhouse leads to global climate change and things of that nature. So, but the good news is carbon dioxide is a precursor for many chemicals. So you can compare to CO, carbon monoxide, which then can be converted to other products. And then methanol and urea, and of course, the trees help us out a little bit with the photosynthesis. Again, MOF is an alternative storage medium. So what is the metal organic framework? Okay, technically it's a porous polymer. Okay, it's a subclass of coordination networks. And then basically what you begin with, you can look at metal cluster plus organic ligands, and then you kind of repeat it. Okay, you repeat it enough, and that's normally how you get the morph. And you can obtain morph in 1, 2, or even 3 dimensions. Most of them are crystalline, some are amorphous, and there are other intermediate ones that display both kind of morphologies. So they are really very complicated to deal with, or to even model. Okay. So the thing about them is they have certain attributes that are easily, or I shouldn't say easily, but can be tuned. So they are tunable. So you look at the surface area, and basically usually they look at the volumetric and the gravimetric. Volumetric is the amount, the unit volume. Sorry, yeah, and gravimetric is the amount per unit mass. Cavity diameter is important. Okay, pore limiting diameter. That's important because it's like it selects for size of the molecule. And then pore volume, that's also very important. Okay. So these are the main geometric features that are usually used within MOFs. So the current opinion really is that physisorption allows for you to put in CO2 or hydrogen and take it out. All right. So I want us to kind of look at this carefully. Okay. So you have, let's say hydrogen. Hydrogen is inside, but then there's also hydrogen at the metal sites and also at the ligands. So think about it very carefully, what that means. So if the hydrogen absorbs very strongly to these sites, what happens when you need to release the hydrogen? You release it, chances are that those that are strongly absorbed on the organic ligand and the metal group, okay, cannot get out. So the first time you use them off, that's fine. Okay, you get a lot of H2 inside. Second time, the amount that you get out of it reduces because the previous time the hydrogen molecules are stuck to the metal centers. So, that should be taken into account when you're trying to select for or design a MOF. So these are some structures, other structures of MOF. The cake-like, there's a boxy type, and this you've seen, and there's this other one here. All right. One thing that I forgot to mention is as follows. Okay, so suppose the metal centers and the ligands are where the hydrogen are absorbed. Well, what else? What about the atoms at the second level? Not on the surface, but the subsurface. What do they do? Do they contribute anything to the function of the MOF? That we don't know. So that's why you need to understand the mechanism of it. So MOF is relatively new application. Technology I said, and there are many evolving application areas, and there are opportunities for PSC as well. So there's of course the gas capture and storage, and H2 and CO2 are the first generation type of molecules to be looked at. People are looking at methane, you're looking at other things. It's used for gas purification and separation. Water remediation, of course. People have started looking at moths for catalysis. And here the idea is to exploit the combination of the metal sites and the functional linkage. I read a paper not too long ago where people were trying to see whether they can use moths for drug delivery. All right? So the issue there is, okay, let's see. Yeah. Oh, okay, got it. So what can the PSC polls here? There's a good representation of PSC people here. So what is it in it for you? Why should you care? Okay, well, when you look at the chemical space, the chemical composition space of moths and the design space is infinite. Okay, and that's an opportunity right there. Tunability. You can look at structural optimization, optimization of process conditions, and for those of you who are interested in modeling, you're looking at AI ML. There are some DFT studies that you can do, reduce other models. The usual techniques that you use in PSC can be repurposed for this kind of application. So, in particular, I have certain aspirational interests as far as moth goes. So I'm interested in geometry optimization through the geometric descriptors. And, down the road, people have been using moths for electronic properties of interest, issues like band gap, for example. DFT and other methods to study storage mechanisms, look at the thermodynamics of it, the kinetic properties of gas moth systems, absorption kinetics, absorption entropies, and so forth. Okay. So what's the question for us today? So the question is, well, I'll get to it in a moment. When you increase the temperature, you increase the pressure and or decrease the temperature, absorption increases. All right. So then the question is, what role do the ligands and the metal centers play in this kind of what roles do geometric features play? So that gets to what I want to talk about, aims and objectives, approach, and some results and some discussions. So actually for this talk only, I'll concentrate on just a mechanistic understanding of moths for H2 storage and CO2 capture. These are things that we're looking at with the people that I'm working with. So there are two main routes of production of moths. The one route is the synthesis method, wet lattice synthesis. Okay. So through electrochemistry, okay, you can synthesize this kind of moth. Through green solvent reflux, you can synthesize this type of moth. But this is not practical to synthesize all moths. There are infinite number of them. The other issue is, a lot of the time, the moths are not stable. And so, synthesizing a stable moth can easily consume one PhD student, assuming they stay around for 4 or 5 years. Okay. So obviously this is not practical. So we need to find more practical ways. So that's why we look at machine learning. And that allows for screening of thousands of moths. And of course, a significant fraction of these moths may not have chemical or thermal stability. In fact, that's one of the things that I discussed with my chemistry department. You talk to them, they say, well, we don't believe in these computational things because eventually most of the results will be useless. All right. So that's a concern. So here's a framework for our moth model, machine learning model. So we use the crystal graph convolutional neural network. This particular one was introduced not too long ago, 2018. Okay, and excuse me. Okay. So the idea is as follows. You have the moth, the crystalline form of it. Let's assume that we're using the crystalline form, not the amorphous form of moth. And then through some operations, you can extract these kind of entities. And then you can put them in some kind of arrays. All right? And then through that, you can get what is called a crystal graph. And you can see that it's a graph, it's a tree. It's not a tree, but it's a graph. And you can see that the edges of the graph go in both directions, right? So then the idea then is to take this crystal graph and then do deep learning convolutional steps. It says R, so you do a certain number of them. Then you let that go through one hidden layer, okay, of elements, neural elements, okay. And then that produces a new crystal graph. This crystal graph is a little bit different from this, okay, because it has much more important information in it. So the way I look at it is, this is your original crystal graph, and this is your latent space crystal graph, okay? So latent space, okay, it can lead to model reduction and all that. Okay. Then you go through some cooling steps, then another hidden layer, and then you get an output. And so, not to bore you with the math, but essentially, this is what you're doing. Those of you doing neural nets, you probably recognize this. This looks like the, so it can be, you can use a sigmoid or something like that. Okay. But they tested this on perovskites, and it worked fairly well, very well. All right. So there's another group that took that idea and looked at it this way. They said, well, why didn't you use the crystal graph convolutional neural net, train a model using thousands of months? Okay. Actually, I think they use about 100,000 months, hypothetical months. You train it. Okay. No, actually, they didn't use months. They used perovskites, other things. They trained it. And then once you have the pre-trained network, you say, okay, how can I use transfer learning to use it to predict months? Okay. And that's what they did in this particular application. Okay. Which is a really neat idea. Transfer learning, if it works very well. If it doesn't, it breaks down, in a way that you wouldn't want to mind. All right. So, okay, so they have this transformer encoder step that they do. So what we did, and this is our deep learning topology, sort of also based on similar ideas. We did not pre-train it, so we didn't use transformer model to try to do that. All right. So what data source did we use? We used the, actually there are many data sources out there. There's a hypothetical mock, and then there's the tobacco database that also includes some mocks, and there's mock FDB. And so we looked at 3 kinds of molecules: hydrogen, carbon dioxide, and methane. All right. And these are the details of our network. I'm not going to go through that. But the important thing that we did was the CGCNN itself only encodes for atoms, things at the atomic length, the bonds, the angles, those kind of things. It does not have geometric features. So what we did was find a way to encode the geometric features into the network. And that's what we did. This is a major step. And that took a while for the students to get this working. So we did some results. I'll get to it in a point in a short time. And then the next step was we wanted to have some kind of a mechanistic understanding of the process. So for which we look at the Sharpe analysis. And basically what that does is it allows us to set the crystal atomic level features, then geometric features on the volumetric deliverable capacity of MOS at various pressures. So I'm going to skip out the details here, but let's just look at it. This is our model structure. Okay. So you know the crystal graph I showed you, the latent space crystal graph that I showed you. we go through several convolutional layers, okay, and then we hook it up to a fully connected network. Now, this time, a lot of the classification work that is done is binary classification. Okay, so we decided to say, well, what if instead of 2 classes, we allow multiple classes? Is there use in that? Okay, so if you wanted to do it for multiple classes, then this is how you put the class labels. So this is class 0, 1, and so forth. Okay. So, but when we're doing the actual testing, we use 4 classes, not 2 classes. So the key idea is, the key points in our model that it incorporates both inorganic polynuclear clusters and organic linkers. So we kind of expanded the kind of linkers that we can have in order to introduce variety into the model. We also, like I said earlier, we incorporate geometric features to enhance the mechanistic understanding of more perform. Okay. We did the multi-class classification, and we did a sharp analysis to try to have a better understanding of the mechanism. So let's look at the kind of metrics that we used in order to train the deep learning. Okay. We always talk about accuracy, precision is important, recall, and the F1 score. Okay. So then we look at 2 pressure levels, a low pressure level and a high pressure level. So for the hydrogen, we look at as low as 2 bar and as high as 100 bar at 30 to 77 degree Kelvin. And then for the CO2, as low as 0.05 and as high as 2.5 at 298 Kelvin. So for each pressure level, okay, we classify the volumetric delivery capacity of each gas in a mole into 7 categories: excellent, good, average, and poor. Okay, so the classes are 0, 1, 2, and 3. All right. So what we hope to do is, within each class, we want to see whether we can learn something. So this is we have lots of results, but I just chose this to illustrate the idea. Okay. So this is the model training and validation. So you can here you can start to see, but we can look at the loss and all those other metrics. Okay, some of the metrics we use, well, here we use only 2 metrics, and all the here we use 5 metrics. And so just going through the training curve, we can say that it's consistent with the kind of numbers that we get from the literature. So these are very highly accurate. Not accurate enough for us, but it's within. It's very, very close. Some are even more accurate than what we have in the literature. Okay. Then next thing we did was to look at the confusion matrix for the model training validation. So we looked at, this shows you 2 bar and 100 bar. Okay. So when you're doing binary classification, things are a little bit easier as far as explaining the confusion matrix. There you have true positives, true negatives, false positives, and false negatives. But when you're doing multi-class classification, it's not as that simple. Things are a little bit more complicated. So what you want to do is look at the true positives, which is on the diagonal, okay, and anything off diagonal, you can consider to be a false positive or a false negative. So when you look at it, so for example, this is more for the students over there. So suppose you have class 0, okay, the true class label is 0, and your prediction is 0, you like it. That's a true positive. So all these are true positives. Okay. One of the things that we noticed when we went to the higher pressures, the true positives were much higher. Okay, and that shows that when we go to high pressures, we're able, our model is much more accurate, tends to be much more accurate. Yeah. So one of the things that we suspect is at high pressure, we have better precision and better recall. Okay, the question is, what explains it? Okay, we feel that probably at lower pressures where the results are less accurate, there's something else going on. Low pressures, maybe the gas molecules absorb very tightly, okay, to the metal centers and the ligands. Okay. Whereas at high pressures, it's not able to do that. So we did a sharp analysis for each class. We have 4 classes, all right? And very quickly, let me explain what this is. So it kind of, the higher the sharp score here, the better, as far as contributing to a particular feature. Okay. So when you look at class 0, you say that these are the geometric features. The geometric features are higher than the 64 crystal features. We're talking about things have to do with the connections, the bonds and all those, the local type of environment. So you look at it and you may conclude that, oh, the crystal features are much more important. Okay, but look at it this way. When you look at the average over the 64 crystal features, you see that the mean crystal feature is for class 0 is 0.011, which is less than any of the geometric features. This is the lowest geometric feature, so it's actually below that. So with that, you can conclude that the geometric features are much more important. Okay, on a geometric feature or crystal feature, geometric features tend to be much more important. Okay. But collectively, the crystal features cannot be ignored. And that's something we saw for each class. Okay. Of course, the cutoff mean crystal feature is different as you go from class 0 to class 3. So overall, I think what we concluded is that be very careful. Don't assume that for morph you need the geometric feature alone. You also need the atoms and the ligands. Because wait, this makes sense. If the atoms and the bonding doesn't affect anything, then technically you can use any morph, right? You just make sure the geometric features are on your side. But it doesn't make sense. We use different morphs, okay? With different ligands, 2 minutes, different ligands and different metal centers. So one of the things, one of the conclusions we can reach is as follows, okay? Take the geometric feature, push it as long as possible, okay? And if you can no longer improve your morph, then look at changing the metal centers and the ligand that you're using. So that's the general conclusion that we can come with. Okay. You can also do B1 plus to further basically certify your conclusions. So when we do the B1 plus, okay. We have crystal feature number 21, which comes on top. And then you have this geometric features, okay, which follow. And then the third crystal features, right? And this is for class 0 and for class 3. Again, they all carry the same story. You cannot ignore the geometric features. You cannot ignore the intrinsic crystal features. Okay, so I think I will skip this slide. This is trying to, we did very many simulations using other people's models and our own model. And this is roughly a comparison of our model to the other. I'm not going to read everything to you, but let's just say that I wouldn't have shown it to you if ours wasn't good. So we did well. Summary, so as more morphs are discovered, the range of possible uses keep increasing. Development of CDCNN-like model for classified morphs That's what we have done so far. And we try to use the Shapley analysis to prove the mechanism of morph. This is something that we can do. And ongoing, we look at DFT, and then the question to David is, can quantum computing help? Okay, this is something that I studied. I don't know the answer. You already told me to forget about that for a moment. So, okay, yeah. So we try to decouple the effects of crystal atomic level structure from the effects of geometric structure. Okay, these are things that we can incorporate later. Transformers allow multimodal modeling, okay, model learning, and also allows you to do, pre-trained transformers and move on. So this is something that we can do. And I'm encouraging the PSC community to try to get on board this, the morph train, okay, before it leaves the station. Okay, I know you guys can do it. So I think I'm about to stop here, but okay. One of the things that I do, one of the research that I do, I collaborate with Dr. Achenie's group. He does electrocatalysis. And so over the last few years, we've collaborated on a lot of, I'm using machine learning and AI in electrocatalysis. And these are some of the products that have come out of that work. Okay. And so that's his group, and I have students. I collaborate with all the group members and these students. And these are relatively new. They've been in the program for 2 years, but they did a month work. So I really applaud them for doing that. Okay. They complain a lot, but they've achieved something. Right. So I think I will stop here. Thank you very much.
Thank you.